And our first speaker is Jonathan Mui from Sydney. So Jonathan, you're here?
Yes, can you all hear me?
Perfect. So please share your screen, and we're looking forward to your talk.
Thank you very much. So I'm glad the microphone was working, because I realized that it wasn't about 10 minutes ago.
Yeah, we hear you perfectly.
Okay, excellent. Okay, let me go over to, oh, you can see a lot of black, but okay, maybe that doesn't matter too much. Okay, somehow I can't use the, give me 1 second. Okay, it's acting a little bit strange, but it'll be fine. Okay, so hello everyone, and I think good morning to most of you, but a good evening to anyone who's watching in the Asia Pacific region. So it's my great pleasure today to speak to you a little bit about asymptotic behavior of solutions to biharmonic heat equations, and in particular, I want to focus in the case of unbounded domains. And this is joint work with Daniel Danners and Jochen Gluck. So the plan here is quite simple. I just want to introduce a little bit of background to kind of motivate the topic, and also to kind of explain how it's connected to some of the other main themes of our conference. And then I want to just present a few details of this qualitative method for obtaining this property known as local eventual positivity of the equation on Euclidean space. And then in the second half of my talk, I want to focus on the analysis for infinite cylinders. So here we have R cross omega, which is a bounded domain with smooth boundary in Rn. So let's begin with some very well-known concepts. So it hardly needs to be said of the important role of the classical heat equation. And here we consider the Cauchy problem. So we have initial datum U0. And it's a very well-known property that it preserves positivity. So if U0 is a non-trivial, a positive function, so here we have to interpret positivity in the relevant sense, then the solution would satisfy that it is strictly positive for all positive times. So again, here, I guess if I borrow some concept from Wolfgang Arendt's talk, this should really be positivity improving. But the situation is quite different when we look at the higher order counterpart. So now let's take a power of the minus Laplace operator. And this is what's known as the polyharmonic heat equation, even though I'm not sure if it has very much to do with heat diffusion anymore. So as the first kind of higher order case, let's look at the biharmonic operator, so minus Laplace squared. And in 2008, there's a paper from Gazzola and Grunau where they prove this result. So let our initial datum be a non-trivial, continuous, and compactly supported function that is a positive. So they observed that the solutions to the Cauchy problem are locally eventually positive. And that means that if you fix any compact subset K of Rn, then we find a time sufficiently large, depending on this choice of compact set and also the U0, such that the solution is strictly positive within this compact set for all times larger than the capital T. And then more recently, in a paper by Ferreira and Ferreira, they managed to extend the above result to polyharmonic and even fractional order equations. So here we have minus Laplace the power alpha, where alpha is just something greater than 1, not necessarily integral. So I think it's just worth taking a closer look at what's going on in this biharmonic heat equation. So I won't spend too much time on this because it's not really the main focus of my talk, but it's kind of nice to see where some intuition may come from. So let's consider the fundamental solution for the biharmonic heat equation. So that means I have a function b of t and x such that the solution to the Cauchy problem is given by a convolution with this b and the initial datum. And in the paper of Gazzola and Grunau, they derive this explicit representation for this higher order heat kernel. And what is really important is that it includes this Bessel function term. And it is known that there are infinitely many zeros of this function. So this is especially transparent in the one-dimensional case where this j of minus half is just up to a constant, the function cosine x divided by square root x. And what's more, they find that on every compact subset, we eventually reach positivity, but then there are always these negative bits that kind of escape out to infinity. So here we have some very explicit work using the, the formula for the fundamental solution, and they do very detailed analysis of this kernel. But from another perspective, we have as motivation a rather recent theory of eventually positive semigroups. So again, it hardly needs to be said, especially at a conference on operator semigroups, that positive semigroups is by now quite a classical topic and very well studied. But here we want to look at eventually positive semigroups, and a systematic theory for that was developed quite recently by Daniel Danners, Jochen Gluck, and James Kennedy. There are two papers from the year 2016. They first have the theory on spaces of continuous functions. So here K is a compact Hausdorff space. And then later they do the same type of theory for general Banach lattices. And the key features of these two papers is that we have basically generalized Perron-Frobenius results extending to these eventually positive semigroups, so not just positive semigroups. And under some smoothing condition on the semigroup, they also obtain what could be called a Krein-Ruttmann converse. And especially from my perspective, what's most interesting is that this theory can be used to analyze eventual positivity for solutions to higher order elliptic and parabolic PDE on bounded domains. So here's the crucial thing, because it is very often assumed that there is a principal eigenvalue that is simple, or in some cases, this is relaxed a little bit, but anyway, the presence of isolated spectral values and poles of the resolvent operator is really quite crucial. And even more recently, we have some work by Sahiba Arora, who has extended the theory to locally eventually positive semigroups, but also with this spectral condition is quite crucial. So, of course, I won't spend more time on this topic because I'm sure we would like to hear from Sahiba and Jochen directly later in the conference. But suffices to say that with unbounded domains, we need some different techniques. So that's the main focus of my talk today. And so I'd just like to highlight some of the key features. And here's the main theorem. So let's consider the biharmonic Cauchy problem. And here we take initial data in L1 intersect L2. And this is because we want to use the Fourier transform and its inverse. And the main result says, well, let's consider the solution to problem 2, the biharmonic Cauchy problem. Then on every compact set, we have this CT times the solution converging to what could be called the fundamental mode of the initial datum. And the convergence is uniform on the compact subset K. And this CT is net, I suppose, that could be seen as a blow-up factor. So this t to the n on 4 here is something that directly counteracts the decay of the fundamental solution. And let me now state how we obtain local eventual positivity from this qualitative result. And it simply suffices to observe that the fundamental mode, the Fourier transform of U0 evaluated at 0 is just up to a constant, this mass, I guess, of the initial datum. And so if we take something that's strictly positive, then this quantity is again positive, and therefore we obtain this local eventual positivity. So as I mentioned already, this is very similar to a classical blow-up analysis where we localize the solution in some compact set and we blow it up so that it is essentially of order 1, so locally constant. So of course, one drawback that I should mention is that this approach does not reveal the time to positivity, which is quite an interesting thing that Gatzola, Grunau, and the other authors that I mentioned were able to obtain. But I presume that this can only be estimated if you have very good knowledge of the explicit formula for the kernel. So I leave this as a question mark whether this can be attained in a less direct way. So, okay, I have to be conscious of time. So I just want to point out some of the main features in the proof. So let's use the Fourier representation of the solution. And this is okay because of our assumption that U0, our initial datum, was in L1 intersect L2. And the really crucial thing is to be able to identify this thing called an approximate identity. So it has this property that, well, it's called approximate identity because it's supposed to be an approximation to the Dirac delta function. Right? So then when we take convolution with a continuous function, we can recover the pointwise value as t goes to infinity. So now we multiply our solution by the blow-up factor, and then we also cut off in frequency space. So we have this zeta of omega function that is a smooth cutoff function, and it's supported around the low frequency, so around 0. And this expression, this integral, can then be interpreted as convolution with this phi t approximate identity evaluated at omega equals 0. And then the remainder term is not so important. We show that it converges to 0. And this is where the convergence takes place, I suppose. So it's a little bit unusual in that we work almost entirely in the Fourier space. Excuse me? Oh, it's all right. Okay. So then I have this family of functions v indexed by x. Right. So the spatial variable comes as an indexing variable, interestingly enough. So just very briefly, we have a net of bounded linear functionals that converges to another bounded linear functional and with appropriate uniform bounds. And it can then be deduced that the convergence is uniform on compact subsets of the appropriate function space. And so this Vx we prove to be a compact family. So, okay, so I should move on to the analysis on the infinite cylinder, which is a lot more interesting. But I just want to make one comment, is that the method didn't really use the fact that we were working with the biharmonic operator. And so we can see that it's not too difficult to generalize to treat the polyharmonic operator. For even more general differential operators, it really, really depends on the symbol that you get after taking the Fourier transform. So here I don't have any kind of big general statements to say, so I'll just leave it as a more or less open question. So now, what is quite new is the analysis on the infinite cylinder. And here we have an initial boundary value problem. So we also, on the domain omega, we equip it with these boundary conditions, which are the natural fourth order Dirichlet conditions. And they're also called clamped boundary conditions because in physical models, it's supposed to represent a plate that's being clamped around the boundary. And we also have this condition on our initial datum so that we may use the Fourier transform for vector valued functions. I am not entirely sure if this can be further generalized to a product space. So now here's the main theorem on the infinite cylinder. And what's important to note is that we assume that the problem on omega, so let's imagine we solve the biharmonic eigenvalue problem on omega, we assume that it has a geometrically simple first eigenvalue. So then we can talk about a unique eigenfunction for this operator. And basically what all this says is that after multiplying the solution by an appropriate blow-up sequence, we have local uniform convergence to this constant times the eigenfunction on our cross-section domain omega. And then along the infinite direction, it is locally constant. So it's kind of a natural thing to expect if you consider the product structure of our domain, right? Because we proved local uniform convergence to a constant on R, but now we also have this cross-section omega. So we have the eigenfunction appearing there. And now here, perhaps you should be a little bit suspicious because what if the eigenfunction E1 is not of one sign, right? This is a fourth order problem. We don't have a maximum principle, so there's absolutely no guarantee that E1 can be chosen to be positive. However, this limit is still well defined, and you'll see why a little bit later. Okay, so the key idea is to do this mixed Fourier representation. So we take the Fourier transform in the infinite direction and then do an eigenfunction series expansion on the cross-section domain omega. So if you write down the operator Laplace squared formally, we can expand it this way. And here, delta y is just the Laplacian in only the y variable. And now I take the Fourier transform in x. So I get this symbol where omega is this frequency variable along R. So for every omega in R, we obtain this boundary value problem that lives only on omega, but there's this parameter omega that goes to infinity. And let's consider the eigenvalues mu n of omega of the operator L omega. And we can associate to these eigenvalues a bunch of L2 normalized eigenfunctions. And a very important technical note is that there exists a choice of eigenfunctions so that the mapping omega going into phi n omega, which is an element of L2, this map is continuous. So we do make use of that in quite a crucial way. And now from a separation of variables, we express the solution to this Fourier transform problem, this eta, by its series expansion. And we have the corresponding Fourier coefficients an. And once you prove that this eta belongs to L1 of R into L2 omega, we can use Fourier inversion, the vector valued version, to write the full solution as this kind of hybrid Fourier transform and series. And so a lot of the work is just to deal with this series and to try and use the techniques we did for the problem on Rn to adapt it to this case. So here, again, I won't say too much, but really the important thing is to have some estimates on how these eigenvalues change with omega. And roughly speaking, they behave like omega to the power 4. And this is what allows us to actually do essentially the same technique as in the Rn problem. So we isolate this first term here, mu1, and we identify an appropriate blow-up sequence so that the CT combined with the exponential of minus t mu1 omega can be used as an approximate identity. So then this first term I1 we treat like the case in Rn, right? So the proof more or less goes through with some extra technical things. And then to deal with this really big ungainly term, this I2, that requires a little bit more technical stuff. So in particular, we want some L infinity estimates on the eigenfunctions depending on omega. So of course, there are many a priori estimates for fourth order problems, even going back to classic papers by Nierenberg, for example. But what we really needed was to understand how this parameter gets involved. And so there are a couple of new things there, I suppose. And okay, so here's the conclusion. After you deal with that remainder series, we show that there is enough decay that that entire series goes to zero. And we are left with convergence to this A1 of zero, and that's the constant C, times phi1 of 0y. And that is the principal eigenfunction on omega. So you see that C is this Fourier coefficient. So if I decide to swap the sign of E1, then you see that the C would correspondingly swap signs. So then this limiting thing is well defined. And what we notice, as I mentioned already, is that the limit is locally constant in the infinite direction, and it resembles the eigenfunction E1 along the cross-section. So this is a rather pleasing result, I guess, because it's kind of what you would expect heuristically. And I would like to finish off by just discussing some really interesting properties of this eigenfunction on omega, because we see that a local eventual positivity on the infinite cylinder depends on the positivity properties of this biharmonic operator on omega, given the nature of this limit. So it turns out that the relation between the domain and positivity of the first eigenfunction is quite complicated. And I mentioned some rather interesting and explicit examples. So we know due to an explicit formula for the Green's function of the operator, on the unit ball, for example, we know that E1 is positive. So that is used, to show that we use the explicit formula due to Bodgil from actually quite a long time ago. And we use the Krein-Rootman theorem as well. So there we have a strictly positive eigenfunction. And Grunau and Sweers in a paper from '97 show that, in fact, you can perturb the ball slightly and the first eigenfunction remains positive. On the other hand, there's another curious result due to Kaufmann, who showed that E1 cannot be positive on rectangles. So there's always a kind of negative deflection of the plate around the corner, is what he showed. Again, though, this is a very explicit paper, so he actually has to work with the explicit form of the solution. So it is not clear on an abstract level why this is the case. And there are many other possibilities. So I just mentioned a couple, and this is really nice survey paper by Sweers that goes into more detail. So it's possible that the first eigenvalue has multiplicity 2 or 3. And this happens on annuli, so with a sufficiently small radius, apparently. And even weirder, I guess, is the first eigenvalue is simple, but is sign changing. So again, this happens on annulus, I think an annulus that's like slightly perturbed, if I remember correctly. So I think as an interesting exercise, you can watch this YouTube video on a plate bending, where you can actually kind of see the sign change. I think this is quite a nice find. I didn't expect to find such a nice explicit demonstration. But yeah, this is quite a nice video if you're interested in these plate equations. So just to close my talk, I just want to say a few words about possible extensions of this result. So what we notice is that on both Rn and on the infinite cylinder, it appears that when you identify blow-up sequence then this CT times the solution converges locally uniformly to what could be called, some kind of eigenfunction. So here, this phi1 is an eigenfunction on the domain omega, but of course it's not really an eigenfunction on the whole cylinder. And then on the Rn problem, it's locally constant. Well, you could say that the stationary solution 1, right, is obviously a solution to the biharmonic Cauchy problem. So in that sense, it is some kind of eigenfunction. 1 is of course not an integral function, but pointwise at least is an eigenfunction of the operator. So this suggests a way to extend this to other unbounded domains, for example, a half space. So if, for example, we could identify something that is an eigenfunction pointwise, but not in a functional analytic sense, this kind of gives you a candidate to look for as a limiting function. So that you might expect that on a half space that the solution after the blow-up argument converges locally uniformly to this eigenfunction that is, pointwise solve the equation, but is not an eigenfunction in, an L1 or L2 space, something like that. So yeah, thank you very much for your attention.
Thank you very much, Jonathan. Are there any questions or remarks from the audience? I guess everyone is looking at the YouTube video now.
Ah, yes.
On the plate bending, yeah. So maybe I have a short question. What do you think you did now for the biharmonic operator, so Laplacian to the power 2? And you say something about more general elliptic operators depending on the symbol. Do you have a class of symbols in mind which could be accessible for the methods?
Yeah.
Or?
Yeah, that's a nice question. So I do have something in mind. So these powers of the minus Laplacian work really well because all you do to modify the proof is instead of modulus omega to the 4, you just have modulus omega to the 2 alpha. So then this tells me that, let's say we have a constant coefficient linear operator where the symbol is a homogeneous polynomial. And then because there's a scaling argument involved, so then if it has this common scaling thing that you can pull out of the integral, then that symbol is a really good candidate for this kind of technique.
Okay, thank you. Further questions?
So maybe one comment.
Yeah,
I think what also works is if you have a polynomial as a symbol which is not homogeneous, but which is a sum of second order monomials with positive coefficients. I think then the same argument works.
Right, okay.
Yeah. So I guess, but I'm not sure. It's quite a long time ago. I thought about it.
Yeah.
Okay. Okay, if there are no further questions, then let's thank the speaker again, and we continue I think in 7 minutes with our second talk. Thank you very much.
All right, thank you.
Nice.